The first family that we're going to talk about is quadratics. So this next sort of, I don't know if you call it a unit, but like the next chunk of what we learn is we have to know how to graph things now. And the reason for this is because at some point, I'm going to put a graph down in front of Zach or an equation and say, hey, Zach, find the inverse of this function. And he's going to find it. And then he's going to graph the function. And then he's going to graph the inverse. And then he's going to be able to say, I can see now visually that the function is an inverse with the other function. So but we can't get there until we know how to graph all the families of functions. So you guys should know this one. How do you graph a quadratic? What's his parent function? Give me a point that's on the graph. How's that? Here, we'll make a table. If I put in 0, but do you understand? Like what I was trying to say here is that if you see me switch back and forth between y and f of x, I just want you to be comfortable with that. They both mean output. 0 gives out an answer of 0. So we all agree that there's a point on here, 0, 0, right? What if I input a 1? It's positive 1, right? 1 squared is 1. So I now know that there's a point of 1, 1. What if I put in a 2? 4. And I'm going to run out of room, so this will be my last one on this side. What if I put in 3, I get out of 9. So this is how, 2, 3, 4, 5, 6, 7, 8, 9. This is how, bless you. This is how the right side do you guys remember what this graph is called? It's called a parabola. This is what the right side of a parabola parent function would look like. And the left side is mirrored because of the nature of this particular function. So if I put in a -1, then -1 squared is of course 1, right? And so then I can just reflect all these points on the other side. So listen, this one I can go pretty quick. I'm guessing you've seen this a lot. That's a quadratic function. And when you graph it, it makes a parabola. Any issues with that? Okay. So the next one I want to talk about with you is a cubic. And I don't think we do this. The last time I had you in class, I don't feel like we graphed any cubics. So again, here's what I know from last year. I taught them how to do transformations. And I taught them like, okay, if you see a +5 over there, it means move it left 5. If you see a -5 up there, it means to go down 5. Like there's all these little shortcutty tips and tricks. But at the end of the day, what my class last year decided was they just like making tables. And I think that's good because that's what upper level math people would expect of you is like when you look at a function, then you're like, oh my God, I don't know what to do. There's nothing stopping you ever, ever from good old fashioned elbow grease, right? And that goes a long ways, as you'll see when we get to our unit on rational functions and asymptotes and all this stuff. Like just having a table, massive. So give me a number. What do you want to put in? 2. 2 is fine with me. What's 2 cubed? 8. So we now know that this cubic function has a point on its parent. I keep calling this the parent, by the way. I should explain that. The moment I modify it, if I put something else in here like x cubed -4, now it's a modified. It's no longer the parent function. The parent functions are the ones where before you mess around and add stuff to them. So 2, 8 is on the graph. So 1, 2, 1, 2, 3, 4, 5, 6, 7, 8. Anyone have any idea what this graph's going to look like just sort of ahead of time? It will be steeper than a quadratic. That's a smart thing to say because the exponentiation is more severe, right? So you're right. But do you have any other sort of ideas as to what's going to change? Is it going to have that parabolic look?
No.
Let's find out. Let's put in 1. What's 1 cubed? Okay. And Zane knocked it out of the park when he said steep. That's a real good observation because, again, a higher exponent causes things to grow more quickly. And then, of course, if we do 0, we get 0. And this is where you start to see for the first time why this does not look anything like a parabola. -1.
Oh, because it's all big like.
Right. So this is an odd function in that, like, now that we have an exponentiation of a negative number, you guys get that like a negative number, if you raise them to a 2, reflects himself back up to positivity, but a -1 to the third power, -1 times -1 times -1, the negatives win the battle and we return a negative value. And the graph actually will come this way. And now that that secret is out, then of course -2 is going to be -8, right? So get used to this. 1, 2, 3, 4, 5, 6, 7, 8. This is what a cubic function looks like. And you will come to hate the process of graphing these. I don't mean to like put words and thoughts into your mouth or mind, but I'm telling you that the act of trying to make these not look like crap takes some. I'm really happy with that one, by the way. I got really lucky. But the steeper graphs are like this, they get really hard to graph. So, anyways, that's what the parent function of cubics looks like. You need to know him. He's the snaky guy, okay? So the cubic is a sneaky guy. Now, what we're going to do is we're going to take the last two families that we just talked about, and we're going to mess with them. What is I hate to say this because it's like cheap and tacky. So if anyone were watching this, they would be like, oh, I got to call that guy. What is like the quote unquote opposite of a square? A root. Good. So the next, and I know I should call it an inverse with big kids like you, but I just thought I'd throw it out there. The next family I want to talk about is this guy. What an interesting fellow he is. So he's like the anti X squared guy. And again, there's no sense in me trying to teach this to you without just making a table. If you learn like five things from me this year, I hope you learn more. I hope you learn a bunch, but if you learn five things, let one of them be this, that if anyone ever gives you a graph and you don't know what to do, make a table. Unless you have a graphing utility where if you were green lighted to just use technology to guide you, then use that. But if someone just said, hey, make me a graph, make a table. Okay. It can't guarantee anything, but it's a great place to start. So let's pick me a number. I would say 8, but I hate it. And why do I hate 8?
This is
Because if I put it in, it's not going to be perfect, is it? And so we have to start thinking when we choose our domain values here about it not being arbitrary. And I would even say on the last graph, it wasn't arbitrary. Like if I'd said pick me an X, and on the first one you said 10, I'd have said that's all fine and good there, Chachi, but 10 squared is 100. And I don't know about you, but I don't want to go up to 100 to make a graph. So we have to be cognizant of like, what are we working with here? Well, I don't want to work with decimals, so give me a good X. I love 4. If I put a 4 in there, what do I get? I get a 2. Give me another one.
60.
16 is fine, but again, I would implore you to think about, do I have enough real estate to the east? And I don't. And should that be a reason to cop out? I don't know, but I don't really want to in this case. I don't want to go to 16. Give me another one.
No.
I like 9. What's the square root of 9? Give me another one. 0. What's the square root of 0? Give me another one. 1. And the square root of 1 is 1. The thing you're going to learn about families of functions is that each one has like its trigger points. Or maybe that's not the right, like its anchor points, points where you go, I know I can count on these guys. And so from this point going forward, your job is going to be to recognize that these are our anchor points for a square root graph. Why can you not give me like -4?
Because exactly 4.
It's an imaginary, right? We can't physically see it on a graph. And so we stick okay, here comes some big kid words. Our domain is restricted. With the last two functions, you could have picked any X you wanted, and the math gods would say, that's fine. I can give you an output. We could do this all day. But with the square root function, it very clearly, I'm going to zoom in on this, it very clearly starts right here. I need you to get that. And this is the first time we've seen a function like this that really kind of gets cut off by an imaginary pair of scissors. So 0, 0 is where the graph sort of spawns. What was another point that we had in our table? 1, 1. Give me another one. 4, 2. 1, 2, 3, 4, 1, 2. And then there was one more. 1, 2, 3, 4, 5, 6, 7, 8, 9, 1, 2, 3. And so you see why, again, 16 would work. It's just not, I'd have to rescale stuff, and I don't really want to deal with that. But this is what my goal for the day is, to get you exposed to these families of functions. And this is what I had it until the end. This is what a square root graph looks like. Oh, crap. Like this. So, some other functions, when we talk about their domains, like for that last one, like a parabola, we could say the domain went from -infinity to infinity. Talk about this function's domain. What is it? It's a hard zero because it gets there. Zero's fine. And then how far right does it go?
Infinity.
Positive infinity, correct. So we start giving more craps about this kind of stuff when our functions aren't just forever left and forever right. If I have time for a couple more, great, but I know I at least have time for one more. Anyhow, that is what a square root function looks like, okay? The next one is, again, it's sort of an inverse thing. The second function that we did together today was y equals x cubed. What's the opposite or inverse of that one?
Three.
Y equals the cube root of x. So this is the fourth family of functions. Again, table, right? Once you memorize it, there's no need for a table, but until you memorize it, it's good. My handwriting is trash today. So give me a number that's good for the domain. I love 8. And 8 sucked for square roots, right? But 8's gorgeous for cube roots because what's the cube root of 8? 2. Jackpot. Give me another one.
7.
Yeah, 27. I don't want to go there. But yeah, I mean 64, right? But realistically, there's only 2 more
0.
on this side. And I got to get rid of these because I'm taking up precious real estate here. I do like 0 because it gives a cube root of 0. And I do like 1 because it gives a cube root of 1. You guys having a hard time? Was it me writing 1 when I said 0 that threw you off your game? Are there more?
Yeah,
No, it's not just the biggers.
There's negatives.
Are there?
Well, if it's a negative, it's imaginary.
It's not imaginary
No,
because
it's just like the cubes.
it is. And the key, what we're gonna learn here is that because the index of the root is odd, that means that negatives are important. You have to ask yourself a question. If you understand roots, then this question will make sense. If I say to you, find for me the cube root of -1, I want to translate that question for you. I want you to give me some number that when you raise it to the third power equals -1. That's what radicals have always been about. It's just what number raised to the power on the outside equals what's on the inside. Is there something you could raise to the third and have it come out as -1? Therefore, the cube root of -1 is -1. And the same goes for like -8, right? Is there a cube root of -8? Heck yeah, there is. It's -2. So the thing I've circled up here in yellow is the key. When we talk about roots, if the index, that's the flavor number, the flavor determiner of the root, if he's odd, then you can do positives, negatives, the whole shebang. Because odd numbers give 0 craps. They can go both ways. So the cube root of -8 is -2. Do you have a picture yet in your mind of what the cube root guy is going to look like?
It's like the cube.
It's exactly what the square root was. He's a flipped version of the cube. And so if you know the cube is a vertical snaky, then you guessed it, this is going to be a laying on its side horizontal snaky. So the 0.82 is right 8 up to 1, 2, 3, 4, 5, 6, 7, 8, 2. I need to really get one of these graphs up here that's like labeled with numbers. And then here's 0, 0, and here's 1, 1. And then it does continue. And that's interesting that the square root version of this kind of had to cut itself off. But this one's like, hey, baby, I'm still going. Like, you can't stop me. And so -1 is right here. And then -8, 1, 2, 3, 4, 5, 6, 7, 8, right here. And so this is, again, just the sideways version of Snaky Boy. Oh, kind of like that.